Before designing large-scale distributed systems, it's important to understand the high-level architecture of the individual computer. Let's see how different parts of the computer work together to execute our code. Computers function through a layered system, each optimized for varying tasks. At the core, computers understand only binary, zeros and ones. These are represented as bits. 1 bit is the smallest data unit in computing. It can be either 0 or 1. 1 byte consists of 8 bits and it's used to represent a single character like A or number like 1. Expanding from here, we have kilobyte, megabyte, gigabytes and terabytes. To store these data, we have computer disk storage, which holds the primary data. It can be either HDD or SSD type. The disk storage is non-volatile. It maintains data without power, meaning if you turn off or restart the computer, the data will still be there. It contains the OS applications and all user files. In terms of size, disks typically range from hundreds of gigabytes to multiple terabytes. While SSDs are more expensive, they offer significantly faster data retrieval than HDD. For instance, an SSD may have a read speed of 500 megabytes per second to 3500, while an HDD might offer 80 to 160 megabytes per second. The next immediate access point after disk is the RAM or random access memory. RAM serves as the primary active data holder and it holds data structures, variables and applications data that are currently in use or being processed. When a program runs, its variables, intermediate computations, runtime stack and more are stored in RAM because it allows for a quick read and write access. This is a volatile memory, which means that it requires power to retain its contents and after you restart the computer, the data may not be persisted. In terms of size, RAMs range from a few gigabytes in consumer devices to hundreds of gigabytes in high-end servers. Their read-write speed often surpasses 5000 megabytes per second, which is faster than even the fastest SSD's disk speed. But sometimes even this speed isn't enough, which brings us to the cache. The cache is smaller than RAM, typically it's measured in megabytes. But access times for cache memory are even faster than RAM, often just a few nanoseconds for the L1 cache. The CPU first checks the L1 cache for the data. If it's not found, it checks the L2 and L3 cache, and then finally it checks the RAM. The purpose of a cache is to reduce the average time to access data. That's why we store frequently used data here to optimize CPU performance. And what about the CPU? CPU is the brain of the computer. It fetches, decodes and executes instructions. When you run your code, it's the CPU that processes the operations defined in that program. But before it can run our code, which is written in high-level languages like Java, C++, Python or other languages, our code first needs to be compiled into machine code. A compiler performs this translation, and once the code is compiled into machine code, the CPU can execute it. It can read and write from our RAM, disk and cache data. And finally we have motherboard or mainboard, which is what you might think of as the component that connects everything. It provides the pathways that allow data to flow between these components. If you'd like to learn more about system design, I recommend watching this video about 6 system design interview concepts next.